Hello, everyone. My name is Marcin. I am a PhD student at ETH Zurich, supervised by Torsten Hoefler. Today, I'm going to present the results of our work on designing a benchmark suite for serverless systems. The big promise of serverless was that the users can give their code to the cloud provider and they can stop worrying about managing any resources and doing scheduling. After all, this is what the name suggests. Serverless, there is no server anymore. However, as it is usually the case, the reality doesn't live up to the expectations. Even though it's serverless, there is still some server, even if you cannot see it, even if it's hidden by several layers of cloud abstractions. And the existence of this server has a significant impact on the performance and cost of our functions and our applications. So let's take a look how a typical serverless system looks like. Here we build an abstract model of a FaaS platform, so we can reason about serverless systems without going into details about specific cloud provider. First, there is a set of servers that are responsible for handling the invocation of user code. In the FaaS programming model, the user submits code as functions. The functions are stateless, so they need to use cloud storage to retain any state between invocations and access additional data. Then the cloud provider is responsible for managing function invocations and finding proper execution spot. And the cloud provider exposes an HTTP frontend with some REST API to allow users to invoke functions. When users invoke a function, the cloud provider selects the execution spot for a function. When there is none, it needs to allocate a new one, and it typically is a container or a virtual machine handling the workload. In that scenario, we have a cold start. This means that we have to pay the performance price of allocating a new resource. If there is a container retained from a previous invocation, we can redirect the function payload directly to that container, and there we have a warm startup. When user submits the invocation, they usually do it through a JSON payload, and they don't need to worry about anything. Everything is hidden from them. Everything happens in the cloud. There are important reasons why we might want to do serverless programming. First of all, we have the pay-as-you-go billing system, which is most likely the most important contribution of serverless. We only pay for the computing and memory resources that we actually use. Furthermore, functions scale quite nicely, and it's much easier to manage the application. On the cloud provider side, the cloud can increase the machine utilization rate and also achieve much better scheduling through oversubscription. However, serverless comes with some significant problems. First of all, as soon as we stop doing infrequent workloads and we start doing some serious computation, the serverless becomes very expensive. The performance also not very consistent. And since the entire system is very black box and hidden from the users, it's very hard to understand what might be going wrong when our functions are running very slowly. And even for the cloud provider, serverless comes with some significant low-level problems. We compared 3 different commercial cloud providers, AWS Lambda, Microsoft Azure Functions, and Google Cloud Functions, and examined different properties of the systems. First of all, by looking at the set of supported languages, we can already guess that the implementation of function workers is different. On some platforms, it's much easier to add a support for new languages. Furthermore, functions need to be usually configured by the user to use a specific amount of memory. And this is also problematic for the users because they need to know at what point, at which memory configuration their function will be most efficient and most performant. Furthermore, there are different models of functions. In AWS and Google Cloud, the functions are just functions allocated in a container, but Azure uses the concept of a function app. A single function app can handle multiple functions, which means that it's more likely for a container with a given function app to be a warm execution place for multiple functions. And finally, the CPU allocation policies are currently binned to the memory, which means that we need more memory. We need more memory to get more computing power. And this is a significant problem for cost efficiency of the FaaS, as we'll see later. There are, of course, other interesting aspects of these different platforms. All of them are compared and discussed in detail in the paper. So since we have a black box system with significant possible differences between cloud providers, we need some way to understand the implications of those differences. And for that, we propose SeBS, an automatic serverless benchmark suite. With SeBS, we provide functions, payloads, and different experiments that invoke functions in a different way to analyze various components of the system. We select few functions, a simple example of a web application that uploads a file to the storage, image processing app, a function that downloads a bunch of files from the storage and returns a compressed file to the user, an example of machine learning inference serving a very important workload in the FaaS that is using ResNet to do image recognition and also scientific application. We present in new insights and results into the performance, cost, invocation latency, and eviction policies of FaaS. First, we begin with performance, where we analyze the cold startup overhead on Google Cloud. And here we found some very interesting results. To analyze the cold startups, we invoke our functions in warm and cold invocations, and we simply take the entire duration of each function and compute the ratio. And the ratio tells us how slower is the actual invocation from the user point of view when we hit a cold startup. In the results, we find a few interesting behaviors. First of all, these overheads are the largest on the machine learning application. Here it comes from the fact that we need to download a huge file from the storage to initialize. This file is the trained machine learning model. And because of that, a cold invocation is 10 times slower. Furthermore, we notice problems with the Node.js implementation in Google Cloud. It simply means that there is really no performance isolation there. And finally, we notice an interesting behavior on all of the functions on Google Cloud, where if we increase the memory allocation, the cold startup actually gets worse. And this is contrary to the results from AWS and also contrary to our intuition. More memory, more CPU power, we should have a slower overheads when doing a lot of initialization work. However, this result aligns with our another finding that the likelihood of function failing to invoke increases with memory allocation on Google Cloud. This indicates that there might be some resource exhaustion problems. Another example, we analyzed resource underutilization. So here we invoke the same functions in the cold and warm startup, and we measure how much resources, the time, compute time, and the memory do we use, and compare it against the billing by the cloud provider. The curve comes from the fact that sometimes we need more computing power, so we allocate more memory, but the functions actually don't need more memory. And this is where we get this problem. Furthermore, there's another problem coming from the granularity of the billing. During that time of experiment, it was 100 milliseconds, which meant that even if the function was running for 5 milliseconds, we're still paying for 100 milliseconds. Since that time, AWS has updated their policies, but on the Google Cloud, we still have the same problem. As a final result, we discussed the eviction policy of containers of AWS Lambda. And here we simply invoke our functions with a given number of invocations. The invocations are concurrent, so always hit different containers. Then we wait for a given period of time and invoke functions again and measure how many containers are still warm. And we invoke this on different combinations of parameters, function configuration, memory, language workers, etc. But what we found out is that this policy is always basically the same. After 380 seconds, the number of active containers is divided by 2. And this is an important analytical model that helps users to invoke functions in such a way that they don't lose performance because of unexpected cold startups. There are more other interesting results that we'll discuss in the second part of the talk, and all of them are in the paper. To summarize, we present an abstract FaaS model and build a benchmarking suite on top of that. We show a new interesting insights into the performance and cost of serverless systems and derive performance models. Our benchmarking suite is available as open source on the GitHub. We will welcome any feedback, feature requests, and pull requests. And since that time, we have expanded the benchmarking suite with support for OpenWhisk. We also implement C++ functions for benchmarking high performance applications, and we're moving towards serverless workloads. Thank you very much for your attention. I'll be happy to take any questions, and we'll see more details in the second part of the talk. In the second part of my talk today, we'll go into more details about how our benchmark suite is designed. And we'll also see more results into the performance invocation latency. Building a benchmark is difficult. Building a serverless benchmark is even more difficult because we're trying to understand performance of the system where we know very little about what is happening inside. We analyze the prior work on this topic and try to combine a list of requirements and good principles for building a benchmark. First of all, the main principles for our benchmark suite is that the benchmark must be usable. So we want the benchmark suite to automatically upload functions, invoke them, and make the measurements. This way, we increase the chance that users receive measurements that can be reproduced. Furthermore, we want everything to be portable between cloud systems, and we want to make the benchmark suite easy to extend with new platforms, new functions, or new experiments. Finally, we want to make sure that the statistical side of our results is sound and the performance models we generate are valid and easy to use for the users. For workloads, we avoid using synthetic microbenchmark and porting applications from other domains, like from high-performance computing benchmarks, because they don't align very well with FaaS. Instead, we analyze literature and the use cases of serverless in the industry to come with realistic workloads. All functions have a single implementation, and then we provide adapters to different cloud interfaces. This way, we have a single implementation, so it's very easy to port to a new platform, but also we always measure the same function. So we are sure that our measurements comparison between different platforms makes sense. Finally, we want functions to express different computational characteristics, for example, different CPU, memory, and I/O usage. We provide a set of metrics to the user. In addition to just measuring computation time from the user perspective, we also query cloud provider logs. We also provide I/O statistics and resource utilization. Finally, we design a set of experiments that measure the performance, the invocation overheads, but also compare our functions against a similar deployment on virtual machines. So using this abstract model of the cloud that we developed and discussed before, we're building our serverless benchmark suite. Basing on the principles that we discussed on the previous slide, we derive our benchmark specification. And this is the list of requirements on the benchmarks and their inputs and the metrics that we want to measure. And so this is done on an abstract level. We only later concretize those functions on specific platforms. In the implementation, we have a kernel driver that runs everything. And it is responsible for managing code and all of the infrastructure. And it provides automatic deployment of functions to the cloud, invocations and measurements, and querying cloud provider logs. In addition, we provide a local environment with Docker where we can measure additional statistics on the functions. And now we go into more details into the results that we present in the paper. So we have already seen some results about the performance, but now we actually take a look at the warm invocations of the functions. And here we found out that in addition to AWS Lambda performing the best on most workloads, as it has been seen also in other works, we also found significant variations on Azure and on I/O intensive functions. So we present 3 functions in this evaluation: the I/O intensive uploader, the image processing with Node.js, and also the ML inference. We invoke the functions and measure 3 metrics: the actual time it took to execute the function as measured in the function, the time measured by the cloud provider, and also the time measured by the user. And we make few interesting observations. First of all, we notice the same problem with Node.js functions on Google Cloud as we did for cloud startups. There's a significant variation, and most likely this is a feature of the implementation. Furthermore, we notice a huge performance variation and also very large tail latency on the uploader functions. This might come from the fact that these are I/O intensive functions, and the I/O bandwidth is also limited by the memory on AWS. And when functions are co-located on the same machine, they start fighting for the same resource. And finally, on all functions, we notice a problem on Azure, except for Node.js. that on the Python implementation, the time it takes to execute the function is much longer than the actual computation time. And this most likely suggests some significant problems in the implementation where there's a very long scheduling delay. Another interesting result in the performance is we compared how much overhead does the serverless add in comparison with a regular virtual machine deployment. So we execute the same function, the same workload on FaaS and on the smallest size of virtual machine on AWS, and we compute the overhead of running the function. And here this overhead varies quite significantly between functions. For example, for the compression benchmark, which needs to download a lot of files from the storage, the storage becomes a bottleneck, and we actually perform quite good on FaaS. However, on some benchmarks, like this GraphBFS, which was invoked with a small payload, and the function execution time is very low, the overheads of invoking a function dominate the time. And finally, we notice that on this IO-intensive or compute-intensive functions, these overheads are quite significant. Finally, it's important to notice that here we also need to run additional experiments to find out the best performing memory configuration for FaaS. So we simply increase the memory size until we find that the functions don't decrease their execution time anymore. Another interesting result we want to present today is in the cost efficiency of functions. And here we try to estimate at what point, at what frequency in our workload, it's more efficient to move to a virtual machine and abandon functions altogether. So for that, we run again the same virtual machine that costs around 1 cent per hour. We compute how many requests this virtual machine can handle in an hour. And then we execute the request on the most economical and the most best performing configuration on FaaS. We compute the cost of running those requests, and also we compute at what point, at how many requests per hour makes more sense to run at a virtual machine. And this also varies again significantly between functions. So for example, for the compression benchmark, which takes a lot of time, only around 300 function invocations per hour, it makes more seconds to consistently run a virtual machine in the background. Another result that we want to present today is the measurement of invocation latency. Also an important problem, as we have seen before. It has a significant effect on the overheads of running FaaS for very fine-grained functions. And here, this is problematic because of the black box nature of the servers. So when users want to invoke a function, they first need to send the payload to the cloud manager. There, the entire allocation is completely black box, and only at some point the execution starts on the function server. And here, ideally, what we'd like to do is simply take time steps on both user and function side and compare them. But we cannot do it in a straightforward manner because the clocks of both systems cannot be aligned. And this is a significant problem in the millisecond scale latency. Therefore, we apply a proven and known clock drift estimation protocol. And when we do that, we can compare the time steps and compare an accurate invocation latency. So we perform the experiments on a varying payload side up to around 6 megabytes, because this is usually the maximum that the functions can handle. And we present the results for cold and warm invocations on all 3 platforms. And here we notice that this time increases into multiple seconds on large payloads, which indicates that there are multiple copies of our input on the way, which also aligns with our FaaS model. And we also find out that the functions called in function invocations on Azure comes with a significant performance variations. So to summarize again, we provide a benchmarking suite that is available as open source, and we kindly ask you to try our software and please give us a feedback if you find interesting and helpful in your research, and we'll be happy to accommodate feature requests and help users to understand the performance implications of the FaaS workloads with our benchmarking suite. Thank you for your attention today.